to a breakthrough. In 1980, he created an equation of his own, one that combined all of the Julius sets into a single image. When Mandelbrot iterated his equation, he got his own set of numbers. Graphed on a computer, it was a kind of roadmap of all the Julius sets, and quickly became famous as the emblem of fractal geometry. The Mandelbrot set.
It's not easy to describe the Mandelbrot set visually. It looks like a man, it looks like a cat, it looks like a cactus, it looks like a cockroach. It's got little bits and pieces that remind us of almost anything that you can see out in the real world, particularly living things. So it has a character that reminds us of a lot of things, and yet it itself is unique and new.
The Mandelbrot set is real, an absolute thing, no question whatsoever. Any mathematician or any computer scientist or student in a school can study it and find the same, describe the same thing. It's a common experience. And so such things that can be magnified forever and have infinite precision do exist, but they're not touchable.
It's a geometrical shape, an icon, if you wish, which somehow embodies as an example a very important aspect of how the world works. Somebody recently actually called this set the thumbprint of God.
With this mysterious image, Mandelbrot was issuing a bold challenge to long-standing ideas about the limits of mathematics.
The blinders came off, and people could see forms that were always there, but formerly were invisible.
The Mandelbrot set was a great example of what you could do in fractal geometry, just as the archetypical example of classical geometry is the circle.
When you zoom in, you see them coming up again, so you see self-similarity. You see, by zooming in, you zoom, 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 you're zooming in, you're zooming in, and pop. Suddenly it seems like you're exactly where you were before, but you're not. It's just that way down there, it has the same kind of structure as way up here, and the sameness can be grokked.
Now we'll begin our serious exploration of the Mandelbrot set. A voyage which, in fact, could last forever and ever, much longer than the lifetime of the universe. I have here the full set, about 6 inches across. Now, if I blow this up, I'll increase the magnification now 13 times, and you'll see more and more detail is appearing. And the interesting thing is you see mini Mandelbrots, replicas, almost identical, yet perhaps subtly different, of the original set. And I can go on doing this. Here's a magnification of more than 3,000 times. So the original picture, about 6 inches across, is now half a mile across. And no matter how much we magnified it, a million times, a billion times, until the original set was bigger than the entire universe, we would still see new patterns, new images emerging, because the frontier, the M set, is infinitely complex. And when I say infinitely, I really mean that. Most people, when they say infinitely, they mean only rather big. But this is really infinity. is so remarkable, in fact astounding, about the Mandelbrot set is that although it's infinitely complex, it's based on incredibly simple principles, unlike almost everything in modern mathematics. In fact, anybody who can add and multiply can understand the principles on which it's based. You don't even have to subtract or divide, still less use logarithms or trigonometrical functions to comprehend how the Mandelbrot set is created. In fact, in principle, it could have been discovered any time in human history and not merely in 1980. But the problem is this: although it's only based on adding and multiplying, you have to carry out those operations millions, billions of times to create a complete set. And that's why it was not discovered until the era of modern computers.
you.